Hi teacher, my name is Warin. Today my group GOGO will present part A, Knowledge and Understanding. And my group will present by this sequence. And today I will present about electron beam lithography, or EBL. EBL is a method of high resolution nanofabrication that uses a concentrated electron beam to create precise pattern on a substrate. It is adaptable and direct right for prototyping and research. Due to proximity effect and charge problem, it is slow and expensive. Electron beam lithography allows for the creation of a wide range of nanopatterns with diverse properties and use. First one is nanodot. This increased by their small diameter, which can range from a few nanometers to several hundred nanometers, and can be formed of metal, semiconductor, or insulators. Nanostructure surface can be made of metal, semiconductor, or polymer, and have diameter ranging from a few nanometers to hundreds of nanometers. Metamaterial, on the other hand, have a diameter ranging from 10 to 100 nanometers and a form of metal and dielectric combinations. Nanowires can be made with the metal, semiconductor, or oxides and have diameter ranging from 10 to 100 nanometers and range ranging from micrometer to centimeter. Finally, photonic crystals are made of dielectric polymer or self-assembled colloid particles and have diameter ranging from 10 to 100 nanometers. Each of these nanopatterns has distinct features and is used in variety of industries, demonstrating the adaptability and potential of EVL in nanofabrication. Numerous parameters influence the EVL process. To begin with, the beam current is critical, as greater current can speed up exposure but result in increased proximity effect and poorer resolution. Second, the accelerating voltage has an effect on the EVL process, since larger voltage can cause scattering and charging effect, which can have a detrimental impact on the final output. Third, the dwell time, or the range of time the electron beam remain concentrated on a certain location determine the exposure. Higher doses and greater feature size can result from longer dwell periods. Finally, the size of the beam point is important, with smaller spot size often contributing to higher resolution and finer feature size. This parameter directly determines the EBL method of overall perform and output quality. The resist material chosen is critical, since it controls the sensitivity, contrast, and resolution of the lithographic process. Another factor to consider is proximity effect, which occurs when electron beam interaction with adjacent feature distort pattern dimension, demanding careful mitigation techniques. The substrate quality also plays a role, with high conductivity substrate, aiding in the reduction of charging effect. Finally, scanning speed influences total process throughput, with faster scanning rate enhancing productivity but potentially reducing exposure accuracy and resolution. Considering this aspect is the critical for improving the EBL process and getting desired lithographic results. And this is a specific material, equipment, and facility required for EBL process. First one is material. We have a substrate, resist material, developing chemical. Next one is equipment. We have a electron beam lithography system, electron beam source, vacuum system, and the last one is substrate handling and positioning. And lastly is facility. We have a clean room environment, ancillary equipment, and a safety measure. And this one is the electron beam lithography system image. Okay, and we have the advantage of EVL. EVL has a high resolution for complicated design at the nanoscale, allowing for the fine control. It provides design freedom by allowing for integrated and customizable pattern. EVL direct write feature provide rapid prototyping and easy patterning changing. It board material compatibility allow it to accommodate a large length of material. Boarding its application when EVL is critical in research and development, since it allows for investigation, testing, and advancements in the nanoscience and nanotechnology. The EVL also have a disadvantage, such as slower processing than other processes, complex and costly equipment requirement, proximity effect that can distort pattern size, shutting effect on insulating material, and restrict throughput for large-scale production. Despite this restriction, EUVL is nevertheless useful for precise nanostructure manufacturing in low-volume production, prototyping, and research application. The last one is the cost of running EUVL system is projected to be around 80,500,000 baht. This includes the price of EUVL system and electron beam source, which went from 15 to 60 million baht, regular maintenance, fabrication, and possible repair cost between 1.5 million and 9 million baht. The cost of facility went between 1 million and 10 million baht, depending on criteria such as size, location, and clean room cost. Consumable energy, labor, and material contribute around 1 million baht. In addition, expenditure is crucial to remember that these statistics are estimated and may change depending on the unique requirement and circumstance of the organization. This is all about the EUVL process.
Next is the XRL, which stands for X-ray lithography. It is a form of photolithography that employs X-rays instead of visible light to create patterns on photosensitive material. There are various steps of fabrication included in XRL technique, such as mask design, etching, and resist removal. This technique can be used to create various patterns, for example, line pattern, dot pattern, grating, and nanowise. Moreover, the size of the product can be varied between nanoscales and micrometer scales. The smallest possible product can be up to 20 nanometers, and the largest can be 1 micrometer. The size and shape of the product from XRL can be affected by many parameters. The first parameter is equipment related, which includes the wavelength of the X-ray, the intensity of the X-ray, and optic and beamline configuration. The second parameter is mask design related, which includes mask feature, size, and intensity, mask alignment, and registration, and mask materials and thickness. The last parameters that could affect the size and shape of the product is resist properties, which depending on sensitivity and contrast enhancement techniques, and resist thickness. In order to create nano product by XRL, many materials are necessary. We will classify the material of the product used with this technique into 3 types. Firstly, the max materials should be heavy metals such as gold, tungsten, and platinum, since these metals have high X-ray absorption capabilities. However, sometimes absorber layers are required in order to enhance the X-ray absorption. Next is the substrate material. The substrate materials is usually silicon, since it has excellent planarity, thermal stability, and compatibility. But if the transparency and thermal properties are required, glass can be used instead of silicon. And lastly, the resist material can be divided into 2 types, which are positive resist and negative resist. The positive resist can increase solubility and allowing the exposed area to be selective, while the negative resist will decrease the solubility and enabling the unexposed area to be selective. The XRL can provide a lot of advantages, such as high resolution due to the X-rays, large field of view, and scalability and pattern flexibility, since various of shape and size can be produced by this technique. However, These techniques still have some disadvantages such as high cost, mask lifetime, and challenging in fabrication of the mask. Since the mask cannot be always used, so we might have to recreate the mask again. And finally, the estimate cost of this technique is quite high due to the mass fabrication. Start with the consumable cost, which can be in range of thousands to $10,000 for each time of fabrication, depending on the requirement of the product and material that have to be used to produce the product. Next is the maintenance cost, which can be in range of thousands to tens of thousands per year, and it's depending on how much the product produced by the machine. Moreover, this technique must be operate under professional supervision, so the labor cost can be in range of tens of thousands to hundreds of thousands per year. And lastly, the R&D and overhead costs can be varied around tens of thousands to hundreds of thousands dollars per year.
Okay, so next lithography method that we are going to present is the extreme ultraviolet lithography or EUVL, which is the recently developed lithography techniques that have been used since 2018 till now, and will be further developed in the futures too. First, the overview of the extreme ultraviolet lithographies. The EUVL is recently developed lithography techniques that have been further developed from the X-ray lithography. Instead of using visible light or X-ray, they use the EUV light instead to create a pattern on the resist material. These extreme ultraviolet light have a very low wavelength, around 13.5 nanometer, which make it can create a very high resolution and very high precision patterns. So it is suitable for creating the nanostructures that are around 10 to 7 nanometers or less, which is used to create advanced technology components such as transistors, capacitors, and interconnects on the surface of the microchips. The EUVL is the currently method to produce most of the largest transistor chips in the market, and it will be the futures of the transistor manufacturing field too. So next is the equipment. On the left picture is the overall process of EUVL. The main principle behind EUV is that we shine the UV light and let it reflect among the mirrors along the way to the mask to create the patterns and reflect it till it's go to the substrate. The first component that we need in order to do the EUV process is the EUV light source that will supply the EUV for the process. Secondly, the second piece of the equipment that we need is the multi-layer mirror for reflecting the EUV light. As the EUV light has a high absorption rate in many material, the mirror need to be composed of multi-layer that swap between the high and the low reflective index material, and this alignment will enhance the reflectivities of the mirrors. Lastly, the EUVL mask is needed in order to create a pattern. This map will have a multi-layer mirror to reflect the EUV and the absorber on the top to absorb the EUV light. Okay, so next is the parameter that we need to consider and control. First is the optic design. The difference in the design between the mirror and the additional of the hole in the system will result in the different numerical apertures, which the greater the numerical aperture is, the better the resolution are. And secondly, we want to minimize the defect on both the mirror and the mask, because those defects can create the change of the reflective pattern or reflective angle, which will result in the bad product that have the false pattern. Okay, third is the layer of the EUV mirror. The different material combination will give the different reflectance, and we want the reflectance to be as high as possible. Moreover, we need to control the thickness of the layer to have the constructive interference to boost the wave output. Then next, we need to make sure that the substrate of the EUV mask is a very low thermal expansion material, because if it is high thermal expansion material, the substrate might expand and change the angle of the light that it reflects. And next, second to last, is the resist material. As the different resist material have a different sensitivity, and we need to control the light edge roughness as low as possible. And lastly, we need to make sure that there are less contamination and debris as possible, as it might affect the mirror effectiveness when they reflect the UV. Overall, the advantage of EUV is it has a good precision and high resolution from the fact that it uses the extreme ultraviolet as a source, and it is very low wavelength, as I mentioned. Secondly, similar to every optical lithography methods, the EUVL is relatively fast method compared to others, which lastly make it suitable for the mass production as it's fast and can create the replicated patterns in a short of time. For the disadvantage, first and foremost, the EUVL is very new and the machine is hard to build, so the machine is currently very expensive and hard to obtain. Moreover, it is sensitive to defects, which small defect on the mirror can create a false pattern, so it needs to control very carefully. And lastly, it is the complex process that need to be precisely designed the optic pattern, so it's very hard to set up the machine. Okay, so the last topic is the estimation of the cost. Overall, the cost of the machine is around 150 to 310 million dollars for each unit. As recently recorded, Intel has ordered the ASML for the next generation of EUVL, and the highest price that they offer is 310,000 million dollars, and the estimated cost of the creating one UMass is around several $100,000. So we can see that the equipment is very expensive in this method. However, the cost of operation of this method is hard to estimate, as this machine is new and expensive. So it is available currently only in the large companies, which they disclose this information due to the business purpose. And that is all for extreme ultraviolet lithography crowd.
The next topic I am going to proceed is focused ion beam lithography. It is one of the top-down approaches that is well known for a high-resolution result. This approach allows for the production of final products with a wide range of sizes in the nanoscale, because the ion beam causes smaller interaction volume, leading to a good resolution to make a very small pattern. The method is suitable for working with materials such as semiconductors like silicon and gallium, as well as metal like silver and copper. However, it depends on the mass of the sample ions where the ion beam can penetrate well or not. At the same energy levels applied to the FIB system, the penetration depth of each material display different results due to the aforementioned reason. However, it is important to note that this fabrication method is more suitable for application with a small penetration depth. It may not be suitable for achieving milling deep patterns with excessively high aspect ratio because of the extended beam tails during the fabrication process, which can result with low resolution. For the affected parameter, firstly, on the ion beam source, both types of ions and the beam size has a huge effect on the fabrication process and results. Different type of ion beam source affect the penetration depth and resolution of the result. For the penetration depth, it is due to the mass of the ion beam source you selected. If it is a small mass like helium, the wavelength will be higher and there will be a large penetration depth and a lot of electron scattering, which causes lower resolution. However, if it is a gallium ion beam, the mass is higher, resulted in lower wavelength, so the penetration depth is lower and have better resolution because the proximity effect will still be negligible. This way, it will be suitable for making small pattern with high resolution. With this parameter, it is the choice to select whether which result you would want to achieve. Another parameter is beam size. Higher probe current leads to the broaden of the beam, which result in poor resolution. Also, larger probe current will reduce current density, which results in lower brightness. Instead, with a small aperture, there will be a smaller beam current, which implies that it is low, but will get a narrow beam, which gives high resolution. For the current density, that might relatively come with the beam size. With a high concentration, there will be a stronger repulsion, causing on energy spread and resulting in bad resolution ultimately. Next is the sample material, which can be separated into the density of the sample and the mass number and atomic number of the sample material. Both of them affects the penetration depth of the ion beam. Focused ion beam lithography depends on the ion-solid interaction, both nuclear process and electronic process, which they refers to the collision of the atom of the solid or the electron with the ion. To briefly speaking, it causes scattering, sputtering, or even implantation for nuclear process and electron scattering for the electronic process. Therefore, the density of the solid atoms and the mass number of them will definitely affect how the ion beam can penetrate through more or less, in which the penetration depth will affect the outcome of the process of the ion-solid interaction. Still, if the penetration depth is high, it will affect the resolution of the outcome as well. For the other parameter, the amount of the energy also has to be concerned. If we compare it with EBL, of course, the energy used will be higher. That is why we could achieve better resolution due to the smaller wavelength. However, compared to itself, with much higher energy does not exclusively imply that it will get a good result. During the process, ion penetrate into the solid material and dislocated atoms are unable to reach the surface. The implanted ions and this displaced atom can be significantly modify the properties of the solid materials. Therefore, the amount of energy must be selected wisely. Lastly, the time of fabrication should be precisely controlled because of the higher energy and high temperature. The fabrication process should not be taking over several hours, otherwise it might damage the targeted material. Also, for the same reason, that is why using the lithography of FIB is suitable for only making small patterns. For the equipment and facility, there will be FIB system, the thin resist, the software and control system for the pattern design, ion source, sample, and substrate, like the silicon wafer, silicon nitride, silicon oxide, and the control environment like the laboratory. For the advantage and the limitation, advantages is a higher solution than EBL, the mass is unnecessary, suitable for small pattern, the proximity effect is negligible, higher resistivity, and a versatile method that can be done in several ways, like for depositioning, for etching, for resist making. And for the limitations, too much pattern is not suitable, complicated and slow process. You have to manually focus the optic system by yourself, and space charge effect that is also cause the limitation, and extended beam tails for lower resolution, limited exposure depth in resist, and the impurity from the source ions, and it costs high, very expensive, and not for mass production. And this is the cost estimation. Mostly it is used for the FIB system.
So the last one is nano imprint lithography. This method is particularly suitable for creating patterns with high resolution and high aspect ratio. It can be used to produce various types of nanostructure. There's four mainly structure that's produced by NIL. So the first one is nanoscale grading. These are predict pattern of lines orange with nanoscale dimension. And the second one is nanopillars and nanovoids. These are vertical structures with nanoscale diameter and height. Third one is nano holes or void. Structure can be created by imprint and subsequent material removal process. And the last one is nanoparticle. It can also be used to create pattern of nanoparticle on a substrate. And as you can see, the right side is the SEM image of this four structure. The next one is parameters. So parameter that affect the resolution, uniformity, and the aspect ratio is pressure, temperature, time, material properties, mole or substrate preparation, demotic force, and UV exposure dose. For resolution, proper control of parameters such as temperature, pressure, exposure dose, and exposure time can improve resolution by ensuring accurate feature replication and reducing process-induced deformations or distortion. For uniformity, careful adjustment of parameters, including temperature, pressure, cooling rate, and some material properties, help achieve uniform feature dimensions and avoid variation across the substrate. And the last one, aspect ratio. The aspect ratio, which refers to height to width ratio of features, can be influenced by parameters such as pressure, stem stiffness, and material flow properties. By optimizing these parameters, it is possible to achieve higher aspect ratio with compromising feature fidelity or inducing defects. So for an example, for pressure, temperature, and time, if it's high, you can gain the high resolution material, but if it's too high, it will affect the uniformity of the material, such as the cracked or it's too hard, too brittle. That's all. And the next part is the specificity. For the materials, there is two specificity that we need to concern. The first one is imprint material, and the second one is substrate material. Second one is the equipment. There's four specificity that we need to concern. First one is imprinting tool. Second one is alignment and positioning system. Third one is the molding system, and the last one is UV exposure system. And the last specificity is facility. There's two that we need to concern, which is the clean room environment and support infrastructure. So it may cause the contamination in the materials or an error in the production if you not follow this specificity. Next is the advantage and disadvantage of the NIL. The advantage, first one is a high resolution patterning. Second one is large area patterning. Third one is cost effective. Fourth one is versatile materials compatibility. And the last one is 3D and multi-layer patterning. So there's also 5 disadvantages. First one is more fabrication. Second one is imprint defects and process-induced damage. Third one is lack of pattern flexibility. Fourth one is sensitivity to substrate topography. And the last one is limit scalability for high volume production. So here's the last part, is the cost of the operation. So as I research, this is the average cost of the production. The first part is imprint material cost. Cost of imprint materials can vary depending on the type of material, supplier, and the application. So it's affect in every cost, depend on your selection. So first part, the imprint material costs around $10 to $1,000 per operation. The mold fabrication costs around $500 to $5,000 per mold. And the consumable and ancillary material costs around $10 to $100 per operation. And the last one is labor costs around $50 to $500 per hour. So the estimate cost is around $570 to $6,600
dollars per one operation. And that's all for our group presentation. Thank you for your attention and see you soon.